So today we're going to be looking at the lengths of curves and surface area. So the types of curves we're going to be looking at are those parametric curves from yesterday. So the ones where you imagine some particle moving around, it traces out a trajectory in space. We want to work out the length of that curve. Okay, so first we're going to derive the equation for it, and then there's a few examples. Okay. In the tutorial, there's quite a few more examples that you can go through, but if you can do these examples, then you should be fine for the test and the exam. Okay, but there are more in the tutorial. Okay, so let's say we've got some curve like this. Yep. Let's say we've got a curve like this in the XY plane. Okay. At this point here, we know that this particle will have some velocity v. So at some starting time to some ending time, it's going to move along the curve. What we want is the length of that trajectory. So let's say here it starts at point P, it ends at point Q. So from time t0 to some final time, what is the length of this section here? Okay. So the way we're going to do that is by not looking at this nice smooth curve, we're going to cut it up into a lot of straight line pieces. So instead of looking at it like this, we're going to look at it like this one here. Okay. So this nice smooth curve, we break up into little line segments, and each line segment has some length, and that's easy to work out. So let's do it for this one here. So we got ourselves a right angle triangle. The length of that segment, we're going to call delta S. Okay, the bottom of the triangle over there, that's going to be delta X. And the top of the triangle there, that's going to be delta Y. Now we can just use Pythag to work out the length of that segment. So we know that delta S squared is going to be equal to delta X squared plus delta Y squared. Well, that's just normal Pythag for that triangle there. Okay, now we're going to rewrite this slightly. Okay, we know that this particle is moving with time. So how far does it go with that delta x? Okay, we can write that as the speed times that little time bit. So whatever the speed of the particle is times that little time bit for that section, that gives us the distance covered. And the same thing for y. So we can write this as delta s squared is equal to delta x by delta t. That's the speed. Dx by dt, that's the speed. Multiplied by the time, that gives us that distance. Yeah. And we have to square it because we got delta x squared. Plus, and then the same thing for y. It's going to have some speed going up. Multiply that by the time, that gives us the distance. So this is going to be delta y by delta t squared, and then delta t squared. Again, this is just speed times time is distance. Okay. Now this delta t squared for both of them, we can factor that out on the right. Okay. We just factor that out. And then finally, to get the delta s, not the delta s squared, we can take the roots on both sides. So this gives us the length of that little line segment at some time. Okay. We multiply it by the little change in time across that length segment, and that gives us the length. Now, what we're going to do is take the limit of these segments getting smaller and smaller. Okay. So here the limit as delta x goes to 0 and delta y goes to 0. Okay, so it's going to be a smaller length segment. So in the limit, delta t goes to 0. So delta t goes to 0, so we're looking at smaller time, so it's smaller and smaller length segments. We're going to have the following. So delta x by delta t. Okay. Right, that's just going to become a derivative. Yeah, if the bottom part goes to 0, we have x plus t plus, say it like this, xt plus delta t minus x of t over delta t. Remember for the derivative. So when delta t goes to 0, this just becomes the derivative. So delta x by delta t, that becomes the derivative, dx by dt. Same thing for delta y by delta t. We can write that as y of t plus delta t minus y of t over delta t. Okay. In the limit delta t goes to 0, this just becomes the derivative of y. Okay. And then that delta t on the outside we can replace with dt. And delta s we can replace with ds. Okay, so it's the normal limiting process we did like with the Riemann sums. Okay, so we end up with ds is equal to the root dx by dt squared plus dy by dt squared dt. So that's the length of the little segment. If we want the total length, we need to integrate this. So the total length is equal to s, and that will be the integral of ds. Okay, so then we just integrate that right inside. Any questions for this? All good. Okay. And then we can rewrite this slightly to what we've seen before. So if we have r of t is given by x of t I hat plus y of t j hat, like we had yesterday, the velocity vector is just the derivative of that. Okay. And then the length of the velocity vector, or in other words, the speed, is given by the length of this vector. Okay. So that's just the speed. That's just the length of the velocity vector. That's the speed. So over here, the length is just the integral of the speed, which we know from before, right? You integrate the speed, you get the length. We've seen that one yesterday for the speed of the particle. All right. Any questions about this? Okay, pretty clear. I'm sure you've seen that in physics, right? Integral of the speed, that gives you your distance. Okay, let's have a look at some examples. So number one. So they're going to be provided in parametric form. So x of t, y of t, z of t. So the first one, we have x is equal to 3t squared and y is equal to t cubed. And we go from 0 to 4. Okay, so maybe like a test type question will be, here's a parametric curve. Sketch the curve, right, like we did yesterday, from 0 to 4. So you sketch the little segment of the curve. And then the follow-up question will be find the length of that segment. Okay. So here at 0, we put in 0. So we get x is 0, y is 0. So it starts at the origin. Then it does some curve going around, ends at 4, at t equals 4. Find the length of that curve. Okay. So homework, do the sketch for that curve like we did yesterday. And then we're going to do the second part, finding the length. Okay, so number one, sketch the curve. Okay, and then number two, find the length of the curve, that section from 0 to 4. So the first part you're going to do for homework, we're going to do the length. So we've got the position as a function of time in terms of x and y. Now we need to find the speed. So we need dx by dt and dy by dt. Okay, and then just a bit of notation. I don't know if you've seen this before. We write this as x dots. Have you seen that before? Yes? No? No. Okay. So you might see that in the textbook. So just in case, x dot is just dx by dt. It's just another rewriting. Okay. So you might see it like that. Okay. So this is going to be equal to the derivative of x. So that will just be 6t. Okay. And then dy by dt. We can also write as y dot. You might see it like that. This is going to be 3t squared. Okay. But to work out the speed, we need dx by dt squared and dy by dt squared, right? For the length of the vector. So let's work out what that's going to be. Okay. And then dy by dt squared. Yeah. So we have that. Okay. Now that we've got that, we can just substitute into that formula, and then we can get the total length. So S is equal to the integral from the starting time to the ending time. So from 0 to 4. And then we have the length of the vector. So that's the root of the x component squared plus the y component squared. So for the x component squared, we've got 36t squared. And the y component squared, that will be 9t to the 4. Okay. Once we're done with all of the deriving and squaring and substituting, this just becomes a normal integral. Yeah, so we go back to our integration techniques from last term. What do we do with that? What can we do? Substitution? Not yet. We can do that later. It's something we can do first. Common factor. What would be the common factor there? What's the common factor? T squared. We can do better than that. 9t squared. No, we can take that out. let's do that. So this will be, right, always try and make it simpler before you do your substitution and stuff. So if you can take out common factors, do that first. So here we have the integral from 0 to 4. So we're taking out a 9t squared, so that will be a 3t on the outside. And then on the inside, we're left with 4 from the first one. And for the second one, just a t squared. Much simpler now on the inside. So now we can do the substitution. So we can let u be this inside part, and then du will be this outside part here. Okay. So let's do that on the side. Okay. On the outside, we've got 3t. Over here, we've got 2t's. That doesn't help us. So let's take the 2 over. Okay. And then we can times both sides by 3, and they'll take care of the 3 dt there. Okay. So that takes care of the u substitution part. Now we need to look at the bounds. So when t is equal to 0, u will be 4. Okay. And then the top one, so when t is equal to 4, u will be equal to, so t is 4 for the upper one, 20. Okay. Please remember to change your bounds. Okay. So this will be the integral from 4 to 20. The 3t dt, that's taken care of by this. So we just have root u. Okay, so 3 over 2, we can take that out. That's just a constant. Okay, integration here, easy. Add 1 to the exponent, that's 3 over 2. Divide by that, that's going to be 2/3. Okay, 3 over 2 and 2/3, that's going to cancel each other. So we just end up with 20 to the 3 over 2 minus 4 to the 3 over 2. You can simplify that a bit more, but I'll leave it like that. Okay. Any questions for this one? Oh, pretty good. Okay, just a note here before we go on. This part here, right, because of all the squaring and stuff, this can get quite complicated, okay, over here with this root. Also, if the x and the y contain trig terms, like if x is sine t and y is cos t and all of that, then this over here is going to have sine and cos terms. It's going to be a trig integral to solve. Okay, so just keep in mind, depending on what's x and y, this over here, you might need a trig substitution, it might be a trig integral. It depends on what's given. So whatever integration techniques we covered before, it shows up again here. Okay. And we'll see that in this next example. So example 2, we have x is equal to 3, cos cubed t, and y is equal to sine cubed t. Right, so x and y contain sine and cos, which means the integral will also contain sine and cos. So it will be a trig integral at the end. Okay, so we've got this parametric curve. We want the length from 0 to 2 pi. Okay. So first thing, we need to find the derivatives. So x dot and y dot, like we had before. Okay, remember your chain rule. So we take the 3 down, so it will be minus 3 cos squared t sine t, and y dot, that will be 3 sine squared t cos t. Yeah. I think this was in the final exam, not last year, the year before. A lot of students forgot the chain rule at the very start here, because you have to do the derivative of the inside. They left it as 3 cos squared, 3 sine squared, and then everything after was wrong. Because your x dot is wrong, your y dot is wrong, then your integral's wrong, your calculation's wrong, all of it's wrong. Yeah, not so great. So please remember chain rule and all of that for when you do those derivatives there. Okay, so x dot squared. So this will be 9 cos to the 4t sine squared t, and y dot squared, that will be 9 sine to the 4t cos squared t. Okay, it's getting quite complicated, but it's not so bad. So we've got the x component squared, the y component squared. Let's integrate up the speed. So the distance s is the integral from the starting time to the ending time. So from 0 to 2 pi. And then we have the speed, so that's the x component squared. Plus, and then the y component squared. Okay. And now this is a trig integral. Okay. From what we did last term. Okay. Quite complicated looking, but we can work it out. What can we do with this? Remember, always try to simplify first before you look at substitutions and all that. Common factor? Yeah? Yeah. Yeah. So here we got 9 sine squared cos squared. Here we also have 9 sine squared cos squared. We can take that out. Okay, good. Okay, so it was all squared, but when we took it out the roots, that goes away. And just a note here, either you can remember this or you need to put it, but the root of something squared is, if I have roots of x squared, it becomes? Yeah? Okay, I think everyone needs to put a note there. It's absolute value. Remember? Roots of x squared is absolute value of x. Okay, please, everyone put that note there. Because here we're going to have an issue with this bounds here. Yeah, so please put a note there. Okay, the problem is with these trig functions, on that interval 0 to 2 pi, we know that sometimes it's positive, sometimes it's negative. If you don't include that absolute value, you're going to be adding up positive and negative values. You'll just get 0. Okay, so please be careful with that. So we'll make a note on the side here. Let's just finish up with this. So we took out 9 sine squared cos squared. So for the first one, we left with cos squared. And the second one here, we left with sine squared. Okay. So let's just make a note about that absolute value. So let's just look at the sine function from 0 to 2 pi. It's the same for the cos. Okay, so this is the sine function from 0 to 2 pi. This is if we didn't put the absolute value, which we need. What is that integral from 0 to 2 pi? Will be 0. Okay. But if we include the absolute value, like we should, this is what it's going to look like. Right. Both parts are now positive. Now it's non-zero. Does everyone see that? Okay. So here, from 0 to 2 pi, if we didn't include the absolute value, we would just get 0. But the particle went somewhere. It can't be 0. So you have to include the absolute value so that you get your positive answer here. Or you need to split it up into parts like this. So instead of going from 0 to 2 pi for that sine graph, you go from 0 to pi and then times your answer by 2. Okay. So you need to think about that. So either you keep the absolute value over here and you go from 0 to 2 pi, but you have to have the absolute value, or you go only over the first bit like this and then times your answer by 2 at the end. Okay, that's how you're going to deal with that. Either you keep the absolute value or you don't have the absolute value, but then you need to change your interval here. Okay. So just put that as a note here for this absolute value with trig functions. Okay. So let's carry on here. So we have the integral from 0 to 2 pi. So we have 3 absolute values sine t cos t. Yep. And then cos squared plus sine squared is 1, so we can just leave that out. Okay. So how do we deal with this absolute value now? So this almost looks like that double angle formula for sine. So let's just do a little bit of working on the side here. So we have sine 2t is 2 sine t cos t. So we just out by this factor of 2. Okay, so we can put that in. Okay. Now we want to get rid of this absolute value. So we're going to integrate over this first portion here, and then just times our answer. So sine 2t from 0 to 2 pi. What is this bit over here? This first bit. Remember, we're changing the frequency here. So if I just have sine, then it's from 0 to pi, and then pi to 2 pi. But if I have sine 2t, I'm doubling up. So how much, what's that distance there for the first little bump? Yeah, I've doubled the frequency. So what will that be? 2 pi? No? Right. There's 2. So from 0 to 2 pi, there's 2 graphs. Okay, draw the little picture. So you got your sine graph. Draw this. And tell me what that bit is there for that first bump. 0 to what? There's sine 2t from 0 to 2 pi. So there's 2 graphs in the same interval, right? Okay, you have to know right frequency and stuff. I can't reteach that. So from 0 to pi, we've got this 1 graph. Now, if we put the absolute value, all of these bumps here are going to be positive. So what's this interval for the first bump? Yeah? Pi over 2. So instead of going from 0 to 2 pi, we're going to go from 0 to pi over 2 and times our answer by 1, 2, 3, 4. Does everyone see that? Okay. So this is going to be 6 integral from 0 to pi over 2 sine of 2t dt. Okay, now the absolute value is gone. We don't need to worry about that anymore. So this is going to be 6. Integral of sine, that's going to be minus cos. Then we need to divide by 2 there. So 6 over 2, that will just be 3 on the outside. Okay. So for the first one, we put in pi over 2. What do we get? Positive. No, I took the half out already. Just one. Just one. Yeah. Okay. And then cos at 0. No calculators. That's a special angle. You're not allowed. Sorry? No, the half's still out. There's just one. Yeah, so this half I already took out, yeah. Yeah, so 1 plus 1. Okay, so we end up with 6. Okay, so please remember that absolute value there. If you didn't include the absolute value, you just get 0. Because this integral from 0 to 2 pi of this, of here, if you drop the absolute value, that integral there is 0. Okay, please make sure you know how to work with absolute values there. Okay. Any questions for this one? All good. Okay. I've got 2 homework problems here for you. Okay, so number 1, we have x is equal to t minus sine t, and y is equal to 1 minus cos t from 0 to pi. Okay, again, there's some trig functions there, so you need your trig identities and all of that. And then number 2, x is equal to e to the t, y is equal to e to the minus t, and z is equal to root 2 times t. Okay, so this one has x, y, and z. So when you're calculating the speed, it will be the root of x dot squared plus y dot squared plus z dot squared. It's the same as your 3D vector length. All right. Any questions for the homework? Yeah, pretty straightforward. Find your derivative, substitute, and then in the first one here, you're going to have some trig integral to solve because of that sine and cos. Any questions before we move on? Yeah, all good. Okay. Let's have a look at the next part, finding the surface area. So finding the surface area is going to be fairly similar to what we did with finding the volume. So remember way back when we did finding the volume, we took some 2D region, we rotated that around an axis, and that gave us a solid. Yeah. So finding a volume. Okay, so let's say we took this region here. So it's a filled-in region. We rotated this around an axis, and this gave us a solid. Okay, So it was a filled-in region. We rotate around, we get a solid. We're going to do a similar thing now, but instead of rotating a region around an axis, we're going to rotate a curve around an axis. Okay, so let's say we have a curve like this. Okay, like y equals x squared, for example. Now, this is not a region. We're not shading any area in. It's just this curve. Yeah, one-dimensional curve. We're going to rotate this around the axis like we did for the volume. And now, since it's not a region, it's a 1D curve, when we rotate this around, it's not going to be a solid, it's going to be a surface. So we're only interested in the surface area here. Okay, shaded in pink there. Okay, that inside part, that's all hollow. We are only interested in that surface. Does everyone see that? If you take a curve, you rotate it around, you end up with the surface here. Does everyone see that? Okay. So please don't mix up your volumes and your surface areas. So here we are not interested in the inside part, it's only the shaded part on the outside. Okay, so how are we going to figure that out? Okay, so it's going to be similar to what we did before. We're going to start off with a very simple example and then figure out what the equation should be. So this is going to be a little bit easier than the volume method. So for the volumes, we had cross-section, disk method, washer method, shell method. We had a lot of derivations for those. Over here, it's just going to be one. It's just going to be one way to do it. Okay, so let's start with a nice simple example. So we're just going to have a straight line segment going along, and we're going to rotate this around the x-axis. We're going to rotate it around, and we're going to figure out some equation that will give us the surface area. So what we're going to do is chop this up into a lot of little bits. Okay, so we've got a line there. We're going to cut it up into little sections. Okay. Each section there is going to have a little length, right? And we know how to find the lengths of curves now. That's going to be ds from what we did before. So ds, that is a small length segment of the curve. Yeah. Same ds from what we did earlier. Now, if we rotate that around the x-axis, what shape do we get? We take a horizontal line, straight horizontal line. We rotate it around the x-axis. Cylinder. Exactly. We end up with a cylinder going around. Okay. Did everyone see that? Okay. So now, again, we're not interested in the volume on the inside anymore. We are only interested in the surface area on the outside. So let's shade that in. So this pink part, that goes all the way around. Okay, so what is the area of that pink part? Okay. So it's just a little piece of a cylinder. we want to work out the area of that. What will that be? If I gave you a cylinder, and I said find the surface area, what is it? Normal cylinder, right? Some radius, some height. What's the surface area? Yeah. Maybe a little sleepy. Maybe if I give you some 10% in the next quiz. Oh, who said that first? Yeah. What is it? 2 pi r h. See, the points. It wakes everyone up. Okay. We'll get your details. Put your student number at the top corner there. Yeah, 2 pi r h. Okay, good. So 2 pi, so that's a 2 there. 2 pi r h, good. So going around here, what will the radius be? Hmm? No. Radius to the axis, like for the disk method. Y. Yeah, exactly. Y. It's the distance from the axis to the curve. That distance is y. Okay, and then h, that's the ds, exactly. Yeah. Okay. So the radius, that's the distance from the axis to the curve. That distance is y over there. And then h, that will be that horizontal distance ds. Does everyone see that? Yes. Okay. So now that's just for that little pink bit. If I want the total surface area, I need to integrate along the x-axis. Everyone see that? Okay. So the total surface area we call capital S. Okay. Don't mix that up with the length S. So capital S for surface area. This will be the integral from the start of the shape on the left. So let's say at A to the end of the shape on the right. Let's call that B. 2 pi y ds. Yeah. Is that clear? Okay. And then remember this ds from before. Now we're going to write this ds slightly different to what we had before. So remember before we had delta s squared is equal to delta x squared plus delta y squared. Okay. That was the same as before. Now, instead of having x and y as functions of time, we're going to write this as y as a function of x, like we have for here. Okay, so a little bit different, but same idea. So we're going to divide through by delta x squared and then times by delta x squared. Same idea as we did with the delta t, but now y is a function of x. So we write it like that. Okay, then we take the roots on both sides, same as we did last time. Sorry, I'm skipping ahead. Yep. And then we do the limit as delta x goes to 0, same as we did last time. So we end up with that for our ds. Is that clear for everyone? Okay, so same sort of steps as before, but instead of x and y being functions of time, now y is just a function of x. That's the only change we're doing here. Now, just a little note here. We could write this a different way, but we always end up with the same answer. It's just a rewriting. So we could write this as ds is equal to the root of 1 plus dx by dy squared dy. Okay. So here, instead of y being a function of x, we write this as x as a function of y. Okay. So when you're doing the calculations, you can use either of these. You get exactly the same answer. It's just sometimes, this might be easier to work with. Okay. But both of them will give you exactly the same answer. Okay. Where'd my page go for the examples? Okay. So let's do, we'll do one example. It's pretty easy. So examples. Number 1. Okay, so we have a parabola, y equals x squared, from the interval from 1 to 2. So it's only this portion over here. Okay, we're going to rotate this around the y-axis. Okay, rotate it around. Find the surface area for that blue part. So this blue part here, that's going to go around. What is that surface area? Okay, so a quick sketch. It's going to look something like this. Okay, if we rotate it around, we end up with this kind of shape. And we want this blue part, so the surface area here. Okay. Okay, so let's see what we get. So we know y is just x squared. Okay. What will the radius be? Remember here, if we go back up a bit, 2 pi radius h. So what's the radius here? From the axis out to the curve? X, yeah. Yeah, so we got the radius is x. And we need ds. Okay, so let's substitute. So we've got y is x squared. So dy by dx, what will that be? This inside part here. 2x. And then we need to square it. So we've got the radius. This ds, that was that little height bit that we worked out. So we can substitute. So that's the integral from 1 to 2. 2 pi times the radius, which we said was x, times that little height bit, which was ds. Dx. Okay. And now it's just a normal integral to do. So here, you can do this a number of ways. So the most straightforward is a u substitution. Right? You let u be this inside part, du will take care of that. Or you could try with a trig substitution if you want the bonus marks. What will the trig substitution be? One plus x squared, the trig sub, tan. Everyone agree? Yeah, you can do a trig substitution with tan as well. I don't recommend that for the test, right? Please do a u substitution first. But, like I said, you do it 2 ways, you get the bonus marks. You can try it out with tan as well. Okay, well, let's just keep things simple here. So u is going to be 1 plus 4x squared. So du, that will be 8x dx. In the front there, we've got 2 pi x, so let's take this over to the other side. So here we have 2 pi over 8. Integral, the bounds. If we put x equals 1, we get u equals 5. And if we put x equals 2, we get u equals 17. So this will be 2 pi over 8, 2/3 u to the 3 over 2 from 5 to 17. Okay, so we get 2 pi over 8, 2/3 17 to the 3 over 2 minus 2/3 5 to the 3 over 2. You can simplify that a little bit more, but that's fine. Okay. Any questions for this example? You're all good. Okay. I've got 2 homework problems for you to try. Okay, so number 1. So I'll give you the curve. You need to find the surface area. So we have y equals root 4 minus x squared from -1 to 1. Rotated around the x-axis. Okay. And number 2, y equals e to the x from 0 to 1, rotated around the x-axis. Please remember to include the sketches as well. All right. Any questions for the homework? All good. Okay, so that's it for this semester. So you look shocked. No, remember, next week's the revision, and then you got your test. So we're done now with the lectures. So for your class test, it will be from what we ended with for the class test 1, okay, just after the integration techniques. We started with applications. So your volume methods, moments of inertia, disk method, washer method, all of that up to here. That will be for the class test. And then the June test will be right from the beginning up to here. Okay. But not everything. Please have a look at that scope. Right, some things have been left out, so please go through that. For the class test, I will put up a more detailed breakdown, but it's pretty much everything that we've covered. Yeah. And then remember, after that, you got your June test, and then I don't see you until 20th of July or something like that. Okay. Just check the dates. It's quite a long mid-year break.